All right, so again, welcome back to this second round of presentations. I hope you're not feeling sleepy. If you are, please stop us at any point. We can, do some other exercise. Justine is an expert at making people not sleep in a workshop. Yeah, she can make you do some yoga while we are on Zoom call, and yep, you'll all be rejuvenated in no time. Okay, so we've just seen some of our own real-time data a minute ago based on heights. Now let's try to make use of the same concepts to sampling. How do we do that? You all remember, let's start, this is where Justine had left us. So in the last presentation, we know that the population is of 300 animals. And in Justine's example, we had surveyed it using 5 sampling units, and we ended up with an estimate of 350 individuals, which of course is off by 50. Now, Justine asked a very valid question, that is it right or is it wrong? Let me, if you guys can make use of a little bit of your polling features, why don't you share on your, not actually polling features, but just raising your hand. So if you can raise your hand when I say this is wrong, if you can let me know how many of you believe that these estimates are wrong. Okay, Iftikhar says we are wrong. Very good. Okay, so, well, in other words, just take this, we need to kind of memorize this by heart. Statistics will always be wrong. It will never be able to give you an absolute answer. In fact, when we just created this, the Lego set and those populations, the probability of a particular value, let's say 183 centimeters, being true for that sample is literally as close as 0. It's a group, it's a bunch of distribution which has a certain probability of being true. Anyway, we'll come to that, but technically all I'm trying to say here is that, oh, how do I move to next slide? Yeah. So if you look at the curve here, it's the same kind of a bell curve, it's the same kind of a histogram that we made with Lego. Here, I have made the same sort of a Lego blocks, Lego stacking with the actual data collected from these sampling units. All I have done to make it a little more interesting, I have repeated this exercise of collecting data from 5 samples 100 times. Now, what we get here is the graph above. If you can, okay, let me use my pen. Annotate. Spotlight. Yeah, what you get here is this little curve. Now, what this curve, just give me a second, please. Right. Okay. What this is showing is that there is a probability, certain likelihood of. Oh, someone else is entering. Justine.
Yeah, I got them. Yeah.
Okay. So what we are saying here is the 95% confidence interval, which is between 2.7 and 4.3. What it really means is that out of 100 or out of 1, there is a 97% chance, 97% chance, 97. Let me put it the other way around. There's 2.5% chance that the actual data or the actual mean would be less than 2.7, and there is 2.5% chance that it could be more than 4.3. In other words, for our estimated mean of 3.5, the value is not what the estimator is saying. It's not 3.5, but it is somewhere between 2.7 and 4.3 with 95% probability. Now, this is a very important point to remember, because many times we have noticed that people use the mean as the absolute truth. That's actually not so. The actual truth is somewhere between 2.7 and 4.3, between this little block, between this value and this value. It's somewhere there. We don't know how much it is, and we may probably never know exactly how much it is, but this is the closest we can get. And if we are able to somehow reduce these errors, we might be able to come up with a better number. Let's look at it with some better examples. Now, in other words, if you remember, we just created those bell curves. If I replace the histogram with a smooth curve, exactly how we did with our Lego grids, we get something like this. What it's showing is there is a very high probability of the value being somewhere here, and a relatively lower probability as we go away from that central value of the mean. Now, instead of randomly placing your sampling units like we are doing here, we can also put uniformly spaced grids. Now, the good thing about wildlife populations is that their movements and their distribution is often random or along a certain gradient. So if you are able to put your sampling in a uniform grid, it is almost as good as random. In other words, the species distribution's randomness or stochasticity is taking care of the randomness of your model, of your sampling design. But sometimes this also becomes much easier to implement out in the field. So a random sample is very similar to a uniform sampling, as one could put it together. Now, what if this distribution of this object of interest, in this case, you see animals are just kind of somewhere on their own, just using the space, almost as if they are like gas particles or little, little particles moving about in the air. What if the distribution of the object of interest is not random, but clumped, or let's say uneven? Can we still go with random sampling? Let us see what it does. So here is a little exercise for you guys. What I have done here is, you remember these values. We're not looking at them right now. But what I've done is I've gone ahead and counted the number of animals in each of these sampling units. And I give those values here. Can I request you all, and I think we do have a sheet where we should be able to do this. Just give me a minute if I can find it easily. Oh yes, there it is. So if you go to the Google Sheets and you go on the sheet called uneven, you should find the same. No, it's not this one. I'll just copy and paste this now. Give me a minute. Actually, that's the one. F, right? Yeah, that is the one. Yes,
it's correct. Yeah,
it's correct, right? I'm so sorry. I'm just kind of losing it. It looks like.
No,
okay.
no, it's good. It's great.
Yeah, so you basically see the same data on over here. Can I request you all to simply estimate the mean, standard deviation, and the confidence? Forget about the confidence limit. Just estimate the mean for me right now. We'll come to the standard deviation and confidence limit later. Don't bother about these two. Don't even do it. Just estimate the mean for me. And the mean is, and each of you may please do it in separate columns. Okay, we already have someone who's filled it, 4.16. Fair enough. Very easy, right? Okay, piece of cake. Anyway, so let me just go back to my presentation. 4.16 can be rounded to 4.2. Now, if you look at something remarkable here, which is the standard deviation, or forget about the standard deviation because it may not be very intuitive at times. Look at the confidence limit, 0.7 to 7.6. What it's saying is my value, my estimate, or the actual number of animals per sampling unit could be anywhere between 0.7 to 7.6. In terms of density, it could be anywhere between 70 to 760, or the abundance could be anywhere between 70 and 760. The density could be anywhere between 7 animals per square kilometer to 76 animals per square kilometer. Now that to begin with, we know there are 300 animals. So our estimate is still not wrong, right? It's just that it's something, you know, over here which is happening, which is really making it very unreliable, or, you know, we're just reporting very wide errors. But ultimately our values are still within the confidence limit. So our actual number is 3, right? And 3 is between 0.7 and 7.6. So even this figure is technically not wrong. All it is doing is there is something else going on. And what's going on, we'll just look into the next 4 slides. So ultimately, what we need to do is we need to figure out a way to decide how good are our estimates. Now, okay, let's again ask you to raise some hand. How many of you do archery or go to a shooting range? Either of the two. Just raise your hand if you do archery or shooting range, or even have darts at home. If the car raises hand, okay. If the car, you there. Who else? Come on, come on, come on. Nobody else? Okay, I do a bit of, I have a dart board to just get my head off a lot of work sometimes. So I do darting at home. So there are 2 people now. Who else? Okay, there are 2 participants who have raised hands. So who are the other participants raising hand? Shoaib, well done. Thank you, Shoaib. And Iftikhar, thank you. And thank you, boss. Great. Okay, so we have only 2 people, including me. There are 3. Okay, we might make a few more people. Justine, I remember you used to do archery, Justine. I know I have
Yes,
a picture, by the way. I'll share a picture of Justine shooting with an arrow. Okay, now let's start. Now let's say this is Justine. Now Justine is an ace shooter. She has practiced right from her childhood. She knows how to hold the bow and arrow. She knows how to take aim. And if she goes out shooting arrows in an archery range, she will end up with the results like this. Now, what do we say about this? If you look at the figure here, let's just focus on the target right now. Justine's results, and the red part here is the bullseye. Now, Justine's results are fairly precise because she's not committing error. She's making a tight little cluster here. The second thing what Justine is doing here is she's very accurate. So as a good shooter, as a good archer, you are supposed to be accurate as well as precise. Now, what if we translate this figure into 2 dimensions? All you need to do is, it's almost, think of it like a target and you're just looking at it on the sides. Now, it may look something like this, where you have more arrows sticking in. This is where you have more arrows sticking in. Let me try to draw something here. Always fun to draw. Yeah. So in case of Justine, she might have had her arrows somewhere like this. So she may have had many arrows here, a few arrows here, and so on. Right? So this is how it may have been the case. Now you see a similar pattern is building up in this case. So very accurate and very precise. That's a good thing. That's exactly how we want our data to be based on our sampling. Now, let's say this is another ace shooter, let's say Iftikhar. Now, Iftikhar is brilliant with shooting. He has a lot of practice, but when he comes to Kyrgyzstan, for example, we end up giving him a slightly defective equipment. Let's say we give him a defective rifle. What he does is, he's so good at shooting, he still makes a very good job of being precise. You know, Iftikhar's shooting is wonderful. He's making very good, he knows how to take aim, and he's making a good show. The only problem is he has a defective equipment, a defective rifle. What is happening here is there is a problem of a bias. So at the end of this exercise, what we are ending up saying is that the actual number, same thing as we did with the previous one, here we are saying the actual average is somewhere around 4, but the reality is 3. Now, because it's very precise, we will end up believing that this is the real value. But what we will never know is that how off it was from the actual target, right? And that's one of the biggest challenges we often face when we do sampling, which ends up being biased. We'll come to that a little later. Now, biased sampling is just like using a defective equipment. You might be excellent with your sampling. You might be excellent with camera trapping. But if you're biasing your sampling, you might end up like this, like Iftikhar did. Iftikhar, no hard feelings. It's not you, it's your equipment. It's the rifle which is defective. So please don't feel bad. I'm just making an example here.
Koustubh, I
All
have a
right.
quick
Now,
question.
yes,
Would
please.
that be the case, for example, if you only surveyed in high mountain areas?
Quite likely. Quite likely. If you're only surveying in a high mountain area, Justine, then you are only sampling that area which has very high density of animals, and you are not really giving an overall picture of the whole mountain systems. So we'll come to that. We have a little slide there a little later to discuss that. So and thanks for bringing up that point. Okay, now let's say this is Shoaib, I feel bad to put you on the spot, but let's say this is Shoaib. Okay. Now, Shoaib is an amateur shooter, and he comes once in a while to a shooting range, maybe sometimes with his girlfriend just to show off, or sometimes he just comes in and practices with the rifle in the shooting range. Now, I would call it like Shoaib is a bit of a newbie. Now, Shoaib is shooting all over the target. He generally has a good idea where the target is, but when you turn the target into 2 dimensions, you will notice that these results are imprecise, right? They're not very precise. We can't say that, oh, this is where the target of 3, average value of 3 is, 300 or 3 animals per sampling unit is. This is, it can be anywhere between, let's say, almost 0 to 5 or something like that. Now, in other words, we cannot say whether it's 1, 2, 3, 4, or 5, but yeah, somewhere here. So again, Shoaib is not wrong. He's a good, he's good. He knows where the target is. It's just that he needs a little more practice, or maybe he needs a lot more sampling to be able to make his estimates a little more precise. Okay, now we come to the last example, which is me. I'm terrible at shooting. I have no clue. I just want to show off that I know how to shoot or shoot an arrow or with the darts. And this is what I end up doing most of the times. You know, I'm all of, not just all over the place, I'm off the target as well. So if you are around me and I'm shooting, please run for your life. You know, who knows, I might end up, you know, by mistake firing at the wrong place. So yeah, so this person, let's say this is me, I have no idea how to shoot a gun or an arrow or a dart. Maybe I've held the gun for the first time. Yep, you better get out of my sight soon, otherwise I might end up hitting you by mistake. Now, again, let's move this into 2 dimensions. What you're noticing here is that the results are wide, so you can't really make any statement whether it's 2, 3, 4, 5, 6, or whatever. And then we also have we are also biased because our mean is somewhere 4, but it could be 3, it could be 5, or anywhere in between. Now, this is a typical situation which we often face when we do surveys. And unless we are ready to design our surveys in a way that we are able to somehow avoid a situation which prevents a shooter to end up in a situation like me, prevents a shooter like how Shoaib's distribution was, or like how Iftikhar was, and try to end up like how Justine's shooting skills were. Ultimately, that's the aim that we want. We want our data to be precise, and we want our data to be accurate. How do we do that? Before that, let's see how can we report. Now, all of this that we have discussed right now can be translated into as mathematics. And don't get overwhelmed by these figures. Many of you might find this as child's play, but in other words, that target practice that we've just looked at can be expressed in numbers. Now, these numbers are more important, much more important than the actual means, because they are a measure of how reliable, usable, and powerful these statistics are. Now, you will see variance is how some people represent error. Standard deviation is nothing but the square root of variance, so they're very closely related. confidence interval we've been working on for a while. You can see it's very easy to calculate if you have either the standard deviation or the standard error. In case you have a standard error, just remove this under root n from below. But basically, these three are very closely connected. What is this? You look closely. It's nothing but a division of the standard deviation by mean. Why is this one of the most widely used and widely compared terms? Is because this gives it standardizes our estimate, our errors. So, and this is typically represented in percentages. So you can say I have a CV or a coefficient of variation of 20%, which means my standard deviation divided by mean is 0.2. I just multiply it by 100 with 100 to get it to 20. So essentially what it means is if you know the mean and if you know the CV, you can always estimate standard deviation. If you know the standard deviation, if you know the mean, you can estimate coefficient of variation, which is a very useful estimator to compare between studies, to compare between different types of data sets, which might vary in the units that they are collected in. Okay, let's move on to the next slide. All right, so as I started, how do we find a way to reduce our error? Now, one of the best ways to reduce errors is to increase the number of samples. Now, you might want to increase, number of samples, and the reason why we suggest that is because of this. Look at the variance, the estimation of variance, standard deviation, confidence in it. Everywhere, n, which is the number of samples, is in the denominator. So if n is bigger, the overall value will be smaller. So at the simplest and the most efficient and effective means to reduce the errors and make your data more reliable with less error is to increase the number of samples. Now you can increase the number of samples randomly or uniformly, it doesn't matter. All you need to do is have many more resources because every sample has a cost associated with it. The other ways of doing them are stratification and modeling. We'll just touch upon them a little later, but we'll come to those in a short while. Now let's start with how do we increase samples. So here we are. You remember this this example we saw a few minutes ago. Justine started with this example. All I have done here is I have increased the number of samples from 6 to 10. Now, if I may, is this an exercise we have on the sheet? Justine, can you kindly check, please, if we have this exercise on the sheet?
Yes, I think we do.
So if you guys could please help come up with the mean, that would be a good starting point. Then we'll take it from there.
It's under the tab increase samples.
Okay.
Koustubh, do you want to share your screen to show that tab so yes, people please. Can see what they're estimating?
This one.
Increase
Okay, we
samples.
already have an answer, 3.3. Fair enough. Okay. Is anybody feeling adventurous enough to estimate standard deviation? Don't worry, if you do, it'll take time, so I'm not going to ask you to do that, but you must try this at home. Use this equation. It's a very simple equation, and it's always fun to try this at home on Excel. So anyway, yes, so we do have an answer of 3.3, which is great. Yeah, it's a very simple thing to do. Let's go back. Right. So when we calculate the mean, look at the standard deviation. What has happened here? If you go back to the one where we had only 5 samples, and now come back and look at this. What has happened here is, if you look carefully, the way standard deviation has reduced. Accordingly, the confidence interval, the 95% confidence interval, has also narrowed down. Now it hasn't narrowed down by much because we've just increased the number of samples from 6 to 10, which is like really nothing. In statistical terms, it really does not much. But if you look at the histogram carefully, you will see a very interesting, with increased samples, the bell-shaped histogram has narrowed down a little bit. It has basically become a little more narrower than it was before. And what it really indicates is, hold on, yeah. What it really indicates is that our sampling has become slightly more precise, a little more precise than what we would have wanted it to be at the beginning. So that's one of the direct benefits you can reap by simply increasing the number of samples. It benefits in very simple terms mathematically by reducing your variance, which means increasing the precision. Now, what happens if I have a distribution of my species which is not even? Let's assume this green little patch here. The green little patch here, these green patches are a certain habitat type. Now, this is typically how most of our study areas are going to be. And when we are sampling this area using the same design as above, as before, what do you get? Now, all I have done is, instead of the species distribution, which was like this, now animals are kind of preferring a certain kind of a habitat. I'm still doing random sampling. You see my number of the sampling units are still where they were. I haven't changed those. They remain exactly where they were. All that has happened is, this is how the distribution is. Now, when I estimate my mean, when I sample this area using the same design as above, what we do is we end up with a similar mean. Now 3.5 has become 4.2. In another sampling exercise, it could have become 3.0 or 2.5 or something. But look at the standard deviation. This has gone wide. It has become 4.36. In other words, my confidence intervals have really bloated from what they were to 0.7 to 7.6. In other words, this is a situation in which Shoaib's target was that it was anywhere between, one extreme in the negative side to another extreme in the positive side. The good part here still is that this is also not wrong. There is still not an error involved in, I mean, the error is fine, but there's no bias still. If you remember, there are 300 animals in this. So 3 should be somewhere here. We are still within the confidence limit. All that has happened is our variance has increased, which means our ability to detect changes has gone down. We are still within the the mean is still within our confidence limit. So the truth is still out there. We still have captured the truth. It's just that we are less confident of what the truth is. We are kind of walking in a dark room. Maybe it's 2, maybe it's 7, somewhere between. But we know, okay, it's between 1 and 8. That's something we can say with a lot of confidence here. Now, one of the usual and the most efficient ways of dealing with such data sets where you have habitat classifying as a certain category is that of stratification. What you can do is you can designate uneven efforts to different strata. In this case, the strata are this green patch is one kind of a habitat. The white patch is a different kind of habitat. What you do is you basically estimate the means separately. You estimate the values and estimate the means and the standard deviations separately. So what you end up here is a mean of 8.5 and 2.6 standard deviation, and you end up with a mean of 0.5 and 0.71. Now remember, this is still very, very high, but that's high not because of anything else, just because we have only 2 sampling units, and that's just pathetic sampling effort. Statistically, you can't just do with 1 or 2 samples. You need even a small sample size is still 5 to 10 sampling units. Below that, you're just randomly hitting any figure, so they won't really make much sense. But yeah, what I've done here is I've quickly gone ahead and I have estimated those values. And what I come up here is by estimating the mean 1, mean 2, I have done a weighted summation, and I end up with a mean of 330 animals across the study area with an error. I'm not reporting it right now. There is an error associated with it. Or the density per square kilometer is 33 with a plus minus error here. Now, what's happened here is my my estimate has gotten closer to reality in some sense, and to some extent the errors have marginally reduced. They may not have reduced as much as I would have wanted, because in one of the strata I had just 2 samples. In a good example, I should have made 3 or 4 samples, and the other one should have 6, 7 samples. But again, this is just for a visual understanding, so please just bear with me on this front. Now, A1 is the area of the first strata. A2 is the area of the second strata, which is the white one. If you use this equation, you will end up with these numbers. And that's one way of estimating or sampling in a situation where your strata are uneven. The example that we did of heights, you might have noticed that we were dealing with a similar situation. We were trying to find an average of heights of human beings, but there is a very strong difference between the average height of men and the average height of women. And that was the difference that was resulting in these 2 peaks. At some point, with a lot of data, we would have still ended up with a uniform peak, but it would have still been somewhere kind of reducing the error by increasing the number. But a simple, cheap way of reducing our errors and coming up with more reliable estimates was by stratification. So the moment we stratified our height data from all participants to men versus women, suddenly we were able to get a more understandable distribution and a more understandable and a narrower confidence limit of our estimates. Just okay. Now moving to the next level. Okay, now here's a question for you all, and please think this through, because this is often going to happen. You may believe there is a particular strata, like let's say someone is sampling for butterflies, and she or he believes that butterflies are distributed in a particular garden, and they believe that their distribution might be much lower around the roadside. But what if there is a particular type of plant which is being planted along the roadside, which is why actually the butterflies are more on the roadside and not in the actual gardens? In other words, what if I thought the strata was like this, which is the yellow patch you're seeing here, but the actual stratification used by the animals turns out to be something like this. Now, please use the chat window and let me know what your answers could be. So you need to answer and let me know what would happen if you have a situation like this, where your stratification was done assuming this is how the animal distribution was, that there were more in the yellow area, fewer in the white area, or the other way around. But it turns out that they were more in this green area, which is totally unrelated to how our stratification has been. What happens in this case? There's no wrong answer, so please, remember, in statistics, everything is wrong or everything is right. So don't worry about answers being right or wrong. There's always a probability of every answer to be right or wrong. So feel free, just try to give your responses. It'll be really useful for us to get to know what you think, because this is going to be an important step. And often we get bogged down, often we get worried about stratification. What if it is wrong? We need to understand.
Sorry,
Yes, please.
Shoaib has had his hand up.
Okay.
Shoaib
So,
Hamid.
Shoaib, why don't you write it down in the chat window for everyone to see? Where is the chat window gone? Shoaib has his hand up. Shoaib, why don't you tell us in the chat window? I'm still trying to figure out how to find the chat window. Ah, there it is. There it is. Okay.
And this happens a lot, Koustubh, right? We plan it, but it's important to try to plan and think about it.
Yes, absolutely.
Right.
Shoaib Sahab, we need your answer.
We also have Joe, Pujir, and Jana. Please feel free to offer any thoughts, whether it's right or wrong.
Okay, just to give you some confidence, till about 1 year ago, I did not know the answer. Okay, Iftikhar, my question is, what if I believe the animal stratification is this, and I plan my survey in a way that I think that, okay, 1, 2, 3, 4, 5, 6, there are 7 samples in this area which I thought was a good habitat, and I only assigned 3 to what I thought was a poor habitat. But in reality, the animal distribution is not aligned according to what my understanding of strata was, but in reality, it's distributed like this. What happens if I have stratified wrongly? What happens if I stratify wrongly? Yeah, that's the question. Joe says estimates have larger error. Okay. Joe, you're absolutely right. Let's see here what happened. Now, in this case, we had the wrong stratification, and I've just done a count here. So I counted all these animals in each of these sampling units. So I end up with these different figures. It's still not wrong. It's just that my errors are wide. That's about it. All I lose is in terms of my errors, but I don't get wrong. I don't end up with a bias. And that's an important thing to remember. One doesn't need to get bogged down by the need to stratify correctly. There are many times you may go with a hypothesis that this is how animals are distributed. When you come back, you realize it was completely different. We're always learning. So I think it's very important to know that in the worst case scenario, if your stratification is wrong, all that it will do is it will inflate your errors to a small extent. There is a slight possibility of bias, but that's something which can be dealt with a good sampling design, and we'll come to it in a few minutes. Okay, is that clear till here? Okay, now we'll quickly change gears to a third type of a situation, which is this one. Now, this is again very realistic. Now, this badly drawn little blue patch here is a river. Okay, now this is our study area of interest. We are only interested in this study area, how the animals are distributed. Now, our animals of interest are distributed unevenly across the study area. There are more animals, or animals are distributed in greater density closer to water, and there are fewer animals away from it. You can see there is some sort of you can see a pattern. There's a thirsty species, just wants to drink a lot. So obviously, when you're close to water, you'll have more of this animal. When you're away from water, you'll have less of this of the species. Now, quite similar is what you would expect with a snow leopard. Along certain altitudes, along certain habitat types of ruggedness, or another parameter like distance from human beings, disturbance, and so on. There could be many factors we can look at. But let's say, what if the situation is this one, where over here, if you look carefully, there is an axis, which is a simple scale in terms of kilometers, 0 to 8 kilometers. And this is how you don't need to call it kilometer, it can be whatever, but this is the scale that we have. As the distance increases, there are fewer and fewer animals away from this river. Now, again, let's go back to our good old random sampling design. It's the same design we have used earlier in this exercise using 10 sampling units. And what I've done is I've just done a count again. What I'm doing now as an ecologist, you could have hypothesized the possibility of a pattern in the animal distribution as a function of distance from the river. Now, you might have, when you were going to these survey units, you might have recorded additional information such as, what was the distance of this point from river? What was the distance of this sampling unit from water? What was the distance of this sampling unit from water? And so on. Now, what I've done is I've just calculated that distance here. And this is the count that I have got. Now, if you look carefully, you will see that, as the distance, let me go to the next slide. Yeah, as the distance increases, there is a reduction in the count, which means as the distance is increasing, I'm seeing fewer and fewer animals getting captured in my sampling units. Now that's good news in a way, because closer to the water, there are more animals. Further from water, there are fewer animals. And I just thought maybe there is a pattern. I went down as a hypothesis, and I'm beginning to see a pattern here. What if I do a simple XY scatter plot? Most of you might know. If you don't, just look at it this way. On x-axis, you put distance. So 0, 1, 2, 3, 4, 5, 6, 7, 8. It's the same distance like this. Okay. On y-axis, you put the count, which is these counts. So for a distance of 0.3, the count was 0.6. So at 0.3 distance, which was, let me draw it here. So 0.3, the count was 6. For the second point, which was 1 kilometer from the river, the count was 5. Okay, do you see it all? Do you all see it here? It's a simple representation of my distance from river and the count on the y-axis. Nothing else. It's just that much. If anybody has a challenge at this step, please raise your hands. We can stop and get back to this. Now, what I'm already seeing here is a bit of an interesting pattern where you see there is sort of a line which is building up. You see, it's almost becoming almost like a line, as my distance increases, my count is reducing. Now, what does that mean? Is there a way I can deal with this a little more elegantly? To me, it looks interesting. As an ecologist, this could be of huge value and interest to a lot of you. So what one can do, there is a very simple way to define this relationship mathematically by something called linear regression. Now, don't worry about the math behind this for now, but you can consider the blue line as the straight line defined by this particular equation. Okay. Now, what does that mean? We'll just do a simple exercise right now. So what I'm saying is that for every distance, if we multiply that distance by 0.9 and subtract it from 5.9, I'll get a count. That almost, honestly, when I first did these models many years ago, I almost found this magical. Now, how can you do that? Let's see if it really works. What I'm going to request you all, use a simple calculator or a pen and a paper, and please use this equation to calculate this number and kindly put it in the chat box. Use this equation to give me a value of count for this distance. In other words, what I will do is 5.9 minus 0.9 multiplied by, what will I write here? 0.3. Can you guys do this and give me the answer here?
We got an answer from Tikar.
Okay, 5.63. All right, well done. Thank you, Iftikhar. Anybody else? Okay, I'll move on. Iftikhar, you're absolutely right. That is exactly what the answer is going to be. Now, can we have someone else please give me the same estimate for this point? Thank you, Rashid. Well done. Very well done. Come on, someone for E, point E. Can you quickly calculate and let me know, please? 3.47. Pooji does that too. Well done, Pooji. Thank you. Yes, you guys are right. Absolutely right. These are the correct answers. 5.63, 3.46, which is rounded to 3.5. Now, just look at these values and compare them with these values. In fact, all of these, I've calculated it for each of them, and they're here. Just look at them. They seem to match pretty well. Getting close to it. Yes, not 100% match, but we don't need a 100% match because we have the errors here. So whenever, again, in this case, the regression line, this is one line, but the line could have been like this, it could have been like this, it could be like this, anywhere in this gray shaded area. So it's like covering our back, it's covering our neck, we don't need to worry about it. If we can plot this error as well, we might be able to say that this little variation that we are seeing between the actual value and the predicted count is fairly similar. They're fairly similar. Now, can I request you all to please use one of the Google Sheets and come up with the mean here of the count and the mean of the estimated count. And if I may show you the file, I think it's this one.
No, the AVD one, I think.
Oh, it's AVD one, sorry. Yeah, there we go. Yes. So you can use this file, and again, I know some of you are super quick. Just quickly give me an average of the two so that we see what values we are looking at. And don't worry if someone else is using that block, you can use another block and just type it wherever you are. The average of count and the average of estimated count. Okay, 3.333, 3.11, well done. All of you, very well done, thank you. So you guys are right. One of you, either I have done something wrong, but anyway, these are the estimates that we get between the two, okay? So ultimately, you look at them, they're very similar. Both the estimates are fairly similar, and they do make similar sense. The errors are slightly wider, but that's all right because ultimately It's just random sampling. These estimates are just random, being treated as random samples, and that's why you're getting these estimates. But yes, you get these estimates, which are fairly reasonable. Now, what we are able to say here, in addition to just telling that this is the density or this is the total abundance of the animal of interest in this study area, is we are able to provide some additional ecologically meaningful knowledge about the particular species. And we are able to comment that, you know, water is an important resource for the species. Now think about it in your ecological terms. These are very valuable findings. Numbers are very valuable, very important. Abundance is very important. But if you are able to improve your understanding beyond just plain numbers, it's almost like you know, an added benefit of your work. And what could be even more useful to an ecologist or a manager to understand the patterns of distribution of a particular species based on actual data, based on empirical data. And this is again going to make it very valuable for your assessment of the species distribution within a sampling area, a study area defined as it is. In other words, what you are able to now say is that the species is found in the study area, and the density is not random, but a function of its distance from the river. Now, here's something even more cooler about models, and which is that with statistics, you need to have data, and you can't deal with missing data. Missing data is discarded. It's of no value. But when you do models, as long as you know your predictor variables are correct, you will be able to predict counts in areas where you have not even sampled. Now, for example, there were two new sampling units. One of them was L and K. We've only done till J. If there was K and L, I know the distance from the river. Can I predict how many animals might be there? Can someone tell me? How many animals should be there in a hypothetical or an imaginary sampling unit K and an imaginary sampling unit L, which are at 3 and 1.5 kilometers from the river? Can someone do this quickly and let me know? This is also there on the Google Sheet for you to do the prediction, I think. Yeah, it's called predict count. So you can use the yeah, you can use the predict count to, oh, I haven't done it, sorry.
We have an estimate coming in, Koustubh.
Okay. There. Yes, Iftikhar says 3.2. And for the other one? Okay. 10 more seconds. For L, for K, Iftikhar has done the right answer. Ranjana, 4.5, maybe not. Or maybe yes. Good. Okay, you guys are absolutely right. Well done. Thank you. I think these are very good estimates that you guys have come up with. Now that's the value of models at times. If you have the right predictor variables, if you can make the right predictions, if you have the right understanding of ecological processes, then you can start using the models to predict data from where you have not even sampled, from where you may not. The only condition and the only important issue you need to keep in mind is that wherever you're predicting should have a similarity, should be similar. All the other parameters in those areas should be similar to where you have used the model, use the data from to create the very model itself. Okay, now last question, and then we'll just have 2 more slides. I think we are a little bit late, Justine. I think we'll be done in the next five minutes or so. Sorry, but yes, what if, now this is a question that Justine you yourself had mentioned in the beginning. What happens if we only sample where animals are? And we won't spend too much time on this. If someone has a quick answer, just type it in the chat window, please. What will happen if we don't have, if we only sample where the animals are?
So for example, only in the very rugged mountains for snow leopards, and avoiding the pastures or slopey areas because maybe they don't really use that area.
Yeah, like in this situation, we realize, this is a great area. I'll end up with lots of animal captures. Let me go and sample here and here. But I know there are some animals randomly moving about, some of those who get kicked out of this nice habitat. They're still there, but I'm not interested. I just want lots of captures. I just want a lot of data. Let me just sample here. What will happen if I only sample in these? Okay, Elias says, excellent. Uzma, well done. Very well done. You guys are all telling the right answers. Thank you so much. We will end up biasing the results, right? And yes, Uzma, we are not getting an overall picture from the field. And that's exactly what happens when we do the actual sampling. Now, I'll not leave you guys to do this right now. You can do it. I think there is an extra sheet on the Google sheet. But the bottom line being that if we do this, we do end up with a significant bias. And how much is the bias? Look at the bias here. We are estimating that there could be 750 animals in a population of 300 animals only because we are ending up sampling in these high density areas. Now, this sounds like I mean, it's a given, right? What's a big deal in knowing this? But you'll be surprised that the global snow leopard estimates that are available today, they are highly biased to the best sampling areas, to the best areas where you will get good captures, where you will get good data from. And that has been one of the biggest challenges that we cannot, even if we have, let's say we have 50 studies from across the snow leopard range, they're not enough for us to be able to project that number to how many snow leopards are there in the world. And that's because currently we are in a situation where we have sampled all of these areas. We may not have even sampled so well, but that 2% of sampling that we talk about, it's biased. If it would have not been biased, then honestly, there are times in several species, even 1.5% or 0.7% of sampling is sufficient, because you don't end up with more errors. You do end up with data which is not as erratic. And if you get a good pattern, then you just stop there. You don't need to go to 20%, 30%. How much sampling is always a subjective, it's not a subjective decision. It's a decision which is dependent on data. So you can make a data-driven decision to decide to make assessment of how much sampling you need to do. But the reason I wanted to emphasize on this slide is because this is exactly what the situation today is with snow leopard sampling across its distribution range, that we have only in majority of areas. Yes, Mongolia is doing an exceptional job over the last 2 years. Pakistan has done exceptional job. Parts of India have done an exceptional job. Apart from that, most places we are ending up with data coming only from the best sites. And that's one of the challenges that we are trying to address in this larger scheme of things with population assessment of the world's snow leopards. Okay. Before I end, I just have two and a half slides, but this is a third what if that I'm coming up to. Now, what happens? This is the same count, same distribution that we started with. Justine started this example. I took from there. I used 5 samples, did 10 samples, 300 animals randomly distributed. Everything goes well. We have a mean of 3.3, confidence limits, 95% confidence limits of 2.7 to 3.9. Nothing changes. What if I end up with something like this? a situation where, because of vegetation or topography or some other factor, if I'm ending up in a situation where I don't count what is actually there. Look at this. This is the actual number, but this is what I'm ending up counting. And I've done an actual counting exercise on this one. Instead of 4, I count, instead of 4, I count 2. Instead of 4, I count 3. 3, instead of 3, I count 1, and so on. Some of them I still count everything, but many of them I don't count well. What I'm doing now is the actual sampling. If I was sampling it in a way that everything was visible, was 3.3 with this confidence limit. Now I've ended up with a count of 2.5 with an error of 1.9 to 3.1. Now, if you look at this, we are actually just touching the real figure. In other words, this is negatively biased, right? So if I show you like this, what's really now happening is that an unknown number of animals is not seen. I don't know how many animals in this population are behind the vegetation. I don't know how many animals are sleeping when I'm doing my survey. I don't know how many animals are hidden or camouflaged behind rocks or within the rocky terrain when I'm sampling my study. Or I don't know how many of the snow leopards living in a study area are never getting photographed during my camera trapping. What is it doing? If I end up capturing, let's say, 20 snow leopards in a study area by using camera traps, I'm saying there are 20 snow leopards, and density is simply count by A. I divide it by A. I will be biasing my results. What I need to do is I need to find a way to correct this count for detection probability. Now, what I need to do is I need to divide my count by a new parameter, which is called P, or detection probability, and that will hopefully correct the figures to make it to make the C closer to N. So N is the real number, C is what I'm counting. Now, if I divide C by some parameter P, a probability, it will fix it and bring my C closer to N, and that will give me the density. Now, that's what I want. The problem is we don't always know what P is. It's an unknown, and one has to use some modeling procedures here to come up with means to estimate it. Again, we are grateful to all the statisticians who've done wonderful work to come up with various extremely valuable and effective means to do this. But this little devil is what we are going to be talking about in the next 3 sessions. And it's this detection probability is what we can also call as the nuisance factor. Some people don't actually want to call it a nuisance factor. They call it an important parameter which can help us understand ecology as well. But having said that, the principles of sampling, stratification, modeling, and errors will remain the same. So the whole purpose of doing this entire brush up to the basics of stats was to get back to the basics and keep those in mind, because whatever we do about detection probability estimation will have something to do with modeling, will have something to do with sampling, will have a lot to do with errors, and will also have something to do with even those histograms that we worked on. So we will be talking about those histograms on many occasions coming in the next few days. But the bottom line being that this last example that we just saw, it's something that's going to take us through in our effort to really end up finding a way to model this unknown little devil that we call as detection probability. So with that, I would like to stop now. Justine?
Ask a question to clarify. So is detection leads to bias, right? Is that also what you're saying? So if we don't take into account detection, we might bias our estimates further.
Absolutely, Justine. Absolutely.
Okay. Great. Thank you, Koustubh. That was
Thank you.
really lovely. And we're so thankful for you taking your time to
So
share with
thank
us.
you all for joining in, and it's going to be a learning experience for me as well. So please.
Yes, please. I mean, everyone, thanks for joining. This is our first time doing these trainings online, which, as you can see, I mean, we keep learning and trying to do better, and we're trying to keep you guys engaged. And I hope you enjoyed and you're still awake, especially Elena, which is, I know it's in the middle of the night for you, so I hope you're still awake. If you are, that's a great sign. And everyone else, thank you for joining. And